Thank you, Marco, and please begin.
Thank you, Andre. Thank you, Emma. I'd like to thank the organizers for putting together this workshop. So yeah, my lab is the Autonomous Systems Lab. In broad terms, in my lab, we work on designing planning and decision-making algorithms for autonomous robots. That is, we work on algorithms that allow robots to make decisions on their own. A specific focus on our research is on designing interaction-aware decision-making algorithms that allow robots to interact with humans. In particular, consider as a motivating example, the example of autonomous driving. Here, for example, I'm showing vehicles that are trying to merge on a highway. While the overall goal of everyone is pretty clear, some vehicles are trying to merge, other vehicles are trying to go straight, there is a lot of uncertainty in the outcome of this interaction. And this outcome oftentimes relies on complex and aggressive negotiations. And I really like a quote from Google to this effect, whereby it is stated that merging into traffic during rush hour is really an exercise in negotiation. And autonomous systems should be able to perform such negotiations for safe and efficient driving. In other words, robots should be able to perform a proactive decision-making. That is, they should be able to proactively interact with other agents to infer their intents, while concurrently exploiting this information to take actions that account for agent responses. Now, my approach in order to enable negotiations for autonomous systems is model-based, whereby a probabilistic model of interaction is used as the basis for policy construction. This is different from model-free approaches whereby actions and associated likelihoods of human responses are only implicitly encoded in a policy that is learned from data. And the claim is that by separating a model for human action and responses from the policy construction process allows us to achieve a level of interpretability that is typically not possible in a model-free approach. Clearly, a key component in a model-based decision-making approach to interaction-aware decision-making is modeling human intent, a modeling framework for human intent. And my work in this area is motivated by 5 key considerations. First of all, we want, in a decision-making setting, we want to have a modeling framework for human intent that will allow us to predict action responses conditional on candidate robot actions. Second, we are targeting decision-making problems with a time scale on the order of about 1 second. This is different from traditional decision-making that reasons about macro actions at the level of multiple seconds, like, for example, should I turn left or right? And this is different from collision avoidance, whereby one has to re-optimize decisions at the level of milliseconds. So we're in a sort of gray area between low-level control and high-level decision-making. Third, at this level of decision-making, uncertainty is generally multimodal. That is, predictions should account for drastically different possible futures. For example, here, I'm considering an example whereby a robotic car depicted in white is driving alongside a human-driven vehicle depicted in blue. And so the question is, if the robotic car were to accelerate, what could be the possible human responses? Well, for example, the human could decelerate, but with some probability could decide to accelerate. So these are 2 drastically different modes that should be accounted for in intent prediction. Fourth, we want to make predictions that are history dependent in order to uncover latent behaviors such as alertness or aggressivity. And finally, we want to have a framework that is as interpretable as possible. Now, typical approaches to intent modeling, such as inverse reinforcement learning, which are referred to as ontological or theory of mind, postulate some structure on how humans make their own decisions. For example, in the form of a cost function that a human is trying to optimize. However, this is typically difficult to reconcile with how humans actually behave. For example, humans are neither cooperative nor adversarial. They're not trying to kill you when they drive around. And this fuzziness of behavior is difficult to reconcile with a theory of mind or ontological approach that is rooted in game theory. Thus, in the past couple of years, we have been investigating phenomenological approaches, where we try to learn directly from data the probabilistic structure of an interaction. That is, the probabilistic structure of human action and reactions and the relative likelihoods, without reasoning about how humans make their own decisions. So that is, without reasoning about the underlying motivations. To do so, we gather data from a driving simulator whereby we have people driving side by side in a variety of interactive driving scenarios. Specifically, we use tools and techniques from generative modeling. Where our work differs from the norm is that we are interested in predicting human intent, not only conditional on the history of an interaction, but also conditional on future candidate robot actions. Specifically, we are interested in learning a probability distribution for the next human action. H here, the subscript H denotes human. Conditional on the history of the interaction, X represents a joint state, for example, in terms of relative positions and speed, and the conditional on past control actions by both the ego vehicle and the other vehicle. But also critically conditional on a future robot action. Subscript R here denotes a robot. Conditioning on the history of the interaction allows us to uncover latent behaviors such as aggressiveness, while conditioning on the future robot actions allows us to capture the interactive aspects of an interaction. In practice, we use a recurrent conditional variational autoencoder model in order to learn such a probability distribution. The end result is as follows. Consider the setting whereby there are two vehicles driving side by side, a human-driven vehicle and a robotic vehicle. The blue line depicts the robotic vehicle, so R. The red line depicts the human-driven vehicle. The way we use this generative model is as follows. We consider a candidate robot future action denoted with a dashed line, and then we probe the generative model in order to see what are the possible responses of a human. And here you see a bunch of possible trajectories that a human might enact. As you can see, so here in the plot, the x-axis depicts time, and the y-axis depicts longitudinal acceleration. So at the beginning, the two vehicles have a 0 longitudinal acceleration, which means they're going at constant speed. And then the question is, if the robot were to accelerate, then coast, and then decelerate, what would be the responses from the human? Here you can see that in most cases, we predict that the human would decelerate, but it's also possible with low probability that the human might accelerate. So the way we use this model for decision-making is to consider a portfolio of motion primitives, basically profiles of different acceleration and deceleration profiles. In actuality, we consider about 4,000 action sequences. And for each one of them online, we generate a distribution of possible human responses. In actuality, we consider about 100,000 human responses. By leveraging GPUs, we can actually generate 100,000 human responses in about a third of a second. So this procedure is actually amenable to real-time computation. So then what we do is for each candidate robot action sequence, we generate a bunch of human responses. And then by using an aggregate cost function that trades off a variety of objectives, such as task fulfillment, safety, collision avoidance, and so on and so forth, then we score the best one. In order to score the best action, we use an expectation. So basically, we average over human responses. Of course, as also brought up by the previous speaker, is of interest to understand and account for risk, which means basically accounting for events of low probability and detrimental consequences, which mathematically means that we would like to exchange the expected value of operator or expected value operator with a risk measure. This is a fascinating topic that I'm not going to discuss today any further, but you can find, if you will, a position paper on this topic on my website. This is topic, so risk-aware decision-making is a topic I worked quite a bit on, and I have a review paper with my former postdoc, Annie Majumdar, available on my website if you are interested. Now, we tested this intent modeling framework along with the decision-making algorithms on the interactive driving simulator that I showed before. Here I'm going to show results for a case whereby a robotic vehicle is trying to swap lane with a human-driven vehicle before a fork. Here you can see a variety of cases. Remember that the white vehicle is the robotic vehicle that is using our algorithms. In particular, these are human-in-the-loop tests, meaning that the blue vehicle is driven by a student. On the left-hand side, you can see predictions in terms of longitudinal velocity and longitudinal acceleration with respect to different possible candidate future robot actions. As you can see, the behavior is quite natural. Of course, we use more rigorous metrics in our paper to assess the validity of our prediction framework. And you can see that some interesting behaviors emerge, like, for example, the robotic vehicle trying to nudge a little bit in the other lane in order to disambiguate intent. So all of this sounds great until a disaster happens. So, for example, this is a case whereby the human, meaning the blue vehicle, defies the expectations of the robotic vehicle and drives into the robotic vehicle. So that will lead to a collision. I will claim that this is unavoidable no matter how sophisticated your intent prediction module is. First of all, intent prediction relies on probabilistic predictions. And sometimes we may get it wrong, as it is the case for a human. Second of all, at this level of decision-making, we are incorporating collision avoidance as a penalty function in aggregate cost function, which might cause conflicting objectives. And finally, as I said, we're able to replan at about 3-4 hertz, but this is ultimately too slow in order to ensure safety. So in order to account for this, we have worked on how to merge interaction planner that reasons probabilistically about future human responses, how to pair such a module with a low-level controller that allow us to reason about interaction even at the lower level of the control hierarchy, but allow us to enforce hard safety constraints. So the low-level controller, it uses techniques from reachability theory and allow us to bridge a gap between probabilistic modeling that is aimed at efficiency and low-level, worst-case adversarial modeling that is aimed at safety. I won't talk any further about this topic. If you're interested in the control side of this work, please join my talk at another ICRA workshop that is going to be on June 13, the PAL workshop. Here, what I want to mention to conclude my talk are a few current directions of research. First of all, we have been working on generalizing our modeling framework to heterogeneous data sets comprising of multiple agents belonging to different semantic classes, such as pedestrians or autonomous vehicles or other traditional human-driven vehicles. Second, we have been working on investigating representation for intent prediction that are cognizant of the downstream decision-making application. And third, we have been working on adding logical structure to predictions, for example, accounting for logical rules, such as rules of the road. I'm only going to briefly discuss the first two topics for the topic entailing adding logical structure to intent prediction, I refer you to a recent paper that we had accepted at Waver. So, as I said, we have been working on generalizing our conditional generative model to the case of heterogeneous datasets with multiple agents in the scene belonging to different semantic classes and also accounting for dynamics. Of course, a pedestrian has dynamics that are very different from the dynamics of a vehicle. A vehicle, for example, is differentially constrained. And we want to account for that in the intent prediction model. The beauty of generative modeling is that it allows us to account for all different conditioning variables in a way that is kind of seamless. We just add these highly heterogeneous information as conditioning variables for the probability distribution that we're trying to learn. So, for example, we can condition on agent dynamics. We can condition on the map, HD map of an environment. There was a related question in the previous talk to this regard. And we can condition on the dynamics of the vehicle. Turns out that increasing the amount of conditioning for your predictions, as also hinted to by Andre in his opening remarks, dramatically improves the quality of the predictions. For example, here, I'm showing you the results of our latest software base called the Trajectron, which is available on GitHub, applied to the new scenes dataset. On the left-hand side, I'm showing you predictions for a relatively crowded intersection. So we have vehicles, we have pedestrians. So on the left side, I'm showing predictions in the case where we do not account for conditioning with respect to the HD map of the environment. So basically knowledge about where the lanes are, where the boundaries of the roads are, and so on. And we do not account for the dynamics of the vehicles. The white line is the ground truth. As you can see, for example, here, our model undershoots the ground truth trajectory because it does not account for the dynamics of a vehicle. In the center figure, I show the case whereby we account for the dynamics of the vehicle as an additional conditional variable. In particular, we model vehicles as constrained unicycles. Here you can see that now the model displays a multimodality, and in particular, we predict that the vehicle could either go to the right or could go straight. But still, we have some probability mass here that spans different lanes, which is not really plausible, and it's due to the fact that we are not conditioning on the map of the environment. Finally, on the right, where we also condition not only on the dynamics, but also on the map on the environment, we have that now the probability mass for our predictions is almost exactly centered around the ground truth. So here's an ablation study that shows how actually conditioning on dynamics and conditioning on environmental maps is very important in order to improve quality of predictions. Finally, and quickly, so far I have been talking about how to predict individual trajectories, which is very good for evaluation and analysis, but it's difficult to use in downstream decision making. For example, you saw that my approach for decision making is to sample, is to consider candidate robot actions, sample the distributions of possible trajectories, and then pick the best one. So this is a very exhaustive search type of an approach that is not very efficient. So the question and what we're working on now is whether we can find prediction representations that are cognizant of downstream control applications. Specifically, we've been investigating system theoretic models of interaction dynamics, whereby we model the interaction as, for example, according to a linear time varying model, whereby X will represent the concatenated state, so the state of the robot along with the state of the other agents. And we want to learn from data the system matrices, so the A matrix, the B matrix, and the C matrix. UR will be the robot action. So to be concrete, consider a 3-agent setting whereby we have a robot, we have a vehicle, and we have a pedestrian. So this is translating into linear time varying model with 3 blocks for the matrices. The diagonal elements depicted in blue represent the dynamics of the agents. So this is not something we have to learn, but the off-diagonal elements, the one depicted in green, represent the action-action interactions. That's what we want to learn from data. So the output of the intent prediction model are not trajectories, are rather system matrices. And since we are in the decision-making control setting, we also account for the action of the robot. We want to learn how the action of the robot influence the actions of the other agents on the road. So this is still work in progress, but the idea here is to consider as an output something that can be readily plugged in typical control approaches such as model predictive control. So to wrap up, the key takeaway message of this talk is that explicit samplable representation of human intent allow for fast and effective intent prediction and decision making. When I started this work back in 2018, generative modeling was not yet widely used for intent prediction. Now this is getting quite a bit of traction, both in theory and in practice. And indeed, together with my student Boris and Karen, we're working on preparing a survey paper on the generative modeling approaches for intent modeling that we're going to submit to the special issue for this workshop. So if you're interested, have a look at this paper. And of course, I want to thank my students, in particular Karen and Boris, who were the main students working on this project. Thank you, and I'll be happy to answer any questions.
All right, Marco, thank you very much. We are a little bit over time, but maybe there is time for one question. In particular, there is one in chat. A question about learning linear time-varying models. How well does it capture interactions that are nonlinear, like inverse square form, for instance?
Yeah, so first of all, this is a linear time-varying model that, so some of the nonlinearity is in a way captured by having a time-varying structure. But the short answer to your question is we do not know yet. This is very recent work. We started from the simplest possible models, which is basically a linear time-varying model that can be considered as a linearization of the nonlinear model at different time steps. But certainly, is this enough in order to achieve the richness of human behaviors that we want to predict to the level of what we had before when we predicted individual trajectories? I don't know. That's the research question.
All right.
Very good question.
Yeah. All right. Thank you very much. This was a wonderful.
And of course, if anyone has additional questions, feel free to send me an email. I'll be happy to reply over email.